Right, good afternoon. So my name is Richard Wilden. I'm the Deputy Head of the Engineering Science Department, and it's my pleasure to welcome you to this year's Morris Lubbock Memorial Lecture and afternoon associated with that. So this is really a celebration of all things engineering, and it's an opportunity for us to, as engineers, engage and for public dissemination, and to talk about things that are of excitement to us as engineers and excitement more broadly across the public community. So we've got a series of talks for you today. In keeping with our the way we run these, we've got a few talks coming from internally, which will report on some of the exciting research and other student activities that are going on within the department. And following that, we have a talk from our invited speaker later on. So I'm going to start by introducing the first two talks. So the first of our talks is going to be given by Dr. Ryan Walker. So Ryan is a mechanical engineer. So he started life as automotive engineering and then worked in Formula 4, Formula 3, Formula 2. He did his PhD in aeronautical engineering at Cranfield, spent about a decade working for Mercedes F1, and joined us in Oxford about 4 years ago as a departmental lecturer. So he leads much of our activity around automotive teaching and research projects, and leads our Formula student activity, which is one of the most popular student activities in the department. So Ryan is going to talk principally about that, I think, and tell us all about what goes on in Formula Student. Great. Ryan.
Thank you very much. Good evening, everyone. Thank you for coming. So, I, as Richard said, have spent a career in motorsport, in various forms of motorsport, culminating in a period in Formula 1. But that's not what I'm here to talk to you about today. I'm here to talk to you about where this all started, for me certainly, and where this all starts for a lot of students, certainly at Oxford and at other universities. And we're going to begin with a little bit of history. So the Mercedes-Benz patent wagon, the first commercially available car, was created in 1885. And a mere 9 years after that, after having created this thing that's going to revolutionize transport, we came to the logical conclusion as a society that what we should do with this is race it. So in 1894, I think, Paris-Rouen was generally accepted to be the first motorsport event that took place. And perhaps the inevitable conclusion of the development of the automobile and of motorsport over the years was that at some point university students would get involved in this. And so it proved to be. So in 1981, students at 4 universities in America got together. They built some sort of car each. They turned up in, I think, a parking lot and went racing against each other. Not terribly successfully, I believe, but the seed was born and it has spiraled into a huge thing. Came over to these shores in 1999 when the Institute of Mechanical Engineers started Formula Student in the UK. And it has really spread into a massive worldwide, phenomena. So it's in Australia, it's in South Africa, it's in South America, all of the continents, big events all around the world. These days there are multiple classes, so you can turn up to concept class, which is where you maybe haven't designed your own vehicle yet. You can design a combustion vehicle using a motorbike engine. Electric vehicle, which is what I'm going to talk about, which is what Formula Student at Oxford does, and also these days AI. So to wind back a little bit, Formula Student is students designing, building, testing, and ultimately racing. They drive it, a little single-seater racing car. We go to Silverstone, that's our big event in the summer. It takes place usually 2 weeks after the Grand Prix, and we have often over 100 teams from all around the world enter the competition. It's really huge. They fly in from everywhere. I think it was won by a team from Spain last year, from Australia the year before, from Italy the year before that. It's really, truly international. So where does Oxford come into this? So I don't know the whole history of racing at Oxford. It might be that sometime in the past before I joined, there was an attempt to run a Formula Student car. But as far as I know, around 2019, some students at the university got together in the Department of Engineering and thought there'd be a great thing for us to get involved in. They managed to prove to faculty that they were serious about it and got a little bit of money, some money funded, and started to build a car. Unfortunately, COVID got in the way a little bit, and so the actual car turned up in 2022. We went racing for the first time. We've grown from about 30 students in the first year rapidly in 4 years. So I have 120 students involved in this. Mostly engineers, but not exclusively. There's important contributions from all across the university. If the physics department ever want to know where their students are, they're probably in the Formula Student Lab. Computer science and mathematics as well, really popular, but also from the humanities. It's open to everybody to get involved in. And I think it's really important that we open this up and let anyone get involved, regardless of their background. This is extracurricular, right? So students build a car, single-seater race car, in a year. Except it's not a year because it's 3 8-week terms. But it's not 3 8-week terms because most of those 3 8-week terms, they are studying for exams, or studying for their lectures, their tutorials, their exams, and so on. And so the fact that students can produce this in that period of time is quite frankly amazing. The graduates from it do go on to Formula One. Every year we've had graduates go into Formula One, but not exclusively that. It's just a great experience for students to take on board and go into whatever they choose to do in life, as you will see later on in this presentation. And last year we commented in 36th overall, but as I'll get into, the overall rankings in Formula Student are perhaps beyond a bit face value. So this is the team in 2022 when we first turned up. Bit of a ragtag bunch on the straight at Silverstone. If you look closely, you will see the gaffer tape and the slightly loose electric wires in the back. Moving on a year, and some carbon fiber has made it onto the car. Someone found an old piece of Ferrari that wasn't needed anymore and repurposed it. Some little bits of aerodynamic development finding their way on there. Oxford Blue makes it onto the car the following year, and most people are now wearing team gear. And finally, we prevail, and everyone's looking smart on the straight at Silverstone. You can see the team has grown as well, so this is obviously the travelling team that go to the event itself. Okay, quickly, the competition. It's 5 days at Silverstone. It's a long event. We spend the first 3 days going through what's called static events. So as engineers, we're always going to have to justify our designs, understand the costs, these days the sustainability, and also do a business plan presentation. And then additionally, the first 3 days are spent going through scrutineering, which strikes dread into the hearts of Formula Students participants, which is getting your car pored over every nut, bolt, line of code, piece of wire to make sure that it's safe to run. All that being well, you then turn up to the dynamic events at the weekend. This consists of a skid pad, so that's a figure of 8, fast as we can, sprint race, 1 lap, acceleration, which is a drag race in a straight line. Endurance, which is the highlight event on the Sunday, which is about 20 kilometers around a circuit. And there's also a fuel economy or efficiency section in that. The eagle-eyed among you would have spotted that I'm saying Silverstone. I've shown you a track on the map that is not Silverstone. That's because we race round a smaller circuit that's placed on Silverstone track. So it's a little bit like a go-kart track. Maybe that's underselling it. That's put up on Copse Corner, usually at Silverstone. Short straights, lots of corners, so we're not driving around the full Grand Prix track like the Formula One cars are. We have a lot of rules. Formula One has changed their regulations this year, as I'm sure a lot of you are aware, and they've made the rule book bigger. A couple of years ago, the number of pages in both the rule books was remarkably similar. The difference being, Formula Student is mostly about safety. We have a lot of rules about safety, but really open in terms of what we can do in terms of design for the vehicle. These are some examples. So there's a roll hoop there. We've got to specify steel bars, and if the car goes upside down, the driver's head won't hit the floor, etc., etc. And then scrutineering. So this is a real challenge. Student-built, particularly electric vehicles, it might not surprise you to know, are not the most 100% reliable of things. The attrition rate is quite high. I think of 120 odd teams, if maybe half of those, say 60, run electric cars, in a good year, maybe 10 of those get to actually run on the circuit and pass through scrutineering. Last year we did so. Unfortunately, we broke down in the race with a broken accelerator pedal, which was a component that was not designed by students. It was bought by students. They did fit it, however, so there is some responsibility there. And as I said, this sort of kind of strikes dread into the heart of the students. Particularly, they've often done the calculations and say confidently that the car is not going to overturn on the tilt test, and then look rather shaky as it goes up gradually on the ramp to a fairly extreme degree. We're laid out much like a motorsport organization, or perhaps any company that you're aware of. They manage this. So as faculty advisor, I'm just that. I don't tell them what to do, I just help them along the way. They manage themselves. They elect a team chief amongst themselves, technical chiefs, leaders of each of the departments, and then the sub-students work on their various sections, much as you would expect in a large company. And not forgetting business, cost, and marketing and sponsorship, which are a huge part of running the team. So now I'd like to talk about the car quickly. So this is the most impressive thing about this. This is this year's car in render form, because as we sit here speaking, the students are in the lab busy working away to put this thing together. So much so that I couldn't take a clean picture of it because there's so many people busy doing bits in there. I'd like to stress how impressive these things are as built by students. So we have 80 kilowatts by regulation from the motor. It's about 107 horsepower. It weighs 260 kilograms. So that gives it 400 odd horsepower per ton. So that's the same as a Porsche 911 GT3, a really fast Porsche. It costs about £100,000. We don't have £100,000 per year. The department kindly give us a donation towards that, but it means the students have to be very clever with what they use, how they manufacture things, what they spend, managing sponsorship deals and so on. We build it from a steel space frame, although we do have carbon fiber, which is made by the students. They do all of the layup. They understand how to design for manufacture. It runs off slick tires. It has an 8.2 kilowatt hour battery, which is built by students cell by cell. It's really impressive. They design it, they build it, they put it all together, they test it, and they ultimately run it. And we use an electric motor from YASA. So for those of you who don't know, YASA, great story, is an Oxford spin-out company who makes some of the world's best electric motors. They're now owned by Mercedes-Benz, and they've kindly sponsored us a unique to us Formula Student electric motor. All this means the cars are fast, but maybe not in the way you think of it. They will do about 60 miles an hour top speed, but they get there really quickly. So this will do 0 to 60 in about 2.4 seconds, which is on par with, I think, a Bugatti Veyron, or pick your hypercar. Remember, designed, built, tested, and ultimately driven by students, right? Little rocket ships. It still amazes me as to how they do this in a year. And so, for this last bit of the talk, I was going to tell you about why this is good for the students and what they get out of it and so on. But I thought actually the best thing to do is let you hear from them themselves. So, if I can get this play.
The Oxford University Racing Team is a Formula student team based at the University of Oxford, where all Oxford University students can join and have the opportunity to build a Formula student car together.
I was looking for an excuse to get into the workshop and do real stuff with my hands, and Formula Students was one of the societies that enabled that for me.
Our engineering course gives us fantastic academic skills, research skills and engineering skills. This gives you a lot of experience as more of a workplace type experience, managing real world projects, and also a lot of soft skills, so a lot of timeline and leadership.
Just a fun way of applying what I've learned while working on an area that is interesting, which is racing and motorsports.
I wanted to kind of develop my practical skills alongside the course. You will find a solution to an engineering problem, make it up in some form of CAD, and model it and iterate on the design, and then you get to see it actually be made.
And that is a serious escape from sitting down at a desk or sitting in a library all day. It really gives you something different to do.
It's social as well, like there's a really good community.
The biggest thing is really the people. You're here to help and here to help out with the car, help other people, and enable them to then contribute more and more to the car. So it's very much this culture that I've fallen in love with.
Knowing people from every year of your course and other courses, other colleges, you get to meet new people as part of a team of accomplishing something.
I've met a lot of engineers and material scientists and physicists through OUR, Like, I'll be walking through the department now and I'll just be stopping every so often to say hello to people. It's really nice.
I think one of the biggest benefits I have experienced being part of the team is that I learned how to apply my knowledge from theories to the practical sense.
I think it's really good to learn from the older students because these people know so much about the actual practicality of it.
I've certainly learned that you don't get everything right every time. You're going to make mistakes, you're going to fall down. I've learned a lot about what it takes to manage big projects, and that type of experience of how to fail and go again, I think is very, very valuable.
The small knowledge of like, oh, if you build a part this way, design a part this way, it'll be so much more easier to machine, so much more easier to like set up and build. Those types of insights you can only really get when you're in a workshop and you're doing it yourselves, like, oh, somebody should have designed it better, like I wish they did this instead of this, and then that kind of sticks, and that kind of, you can then carry that forward.
I feel it's so cool that we can actually build a functioning car from our hands, like all by the students.
Like you're keeping different parts of your like mind active, working on different things. It's just fun.
But 100% the competition is the highlight of this whole thing. It's a big challenge, you learn a lot, but when you actually get to take the car to Silverstone and compete against the other unis, you get to meet the other teams and see what they've done, that's one of the highlights of my year.
That's it. Thank you very much.
Can I ask an unfair question, which is where do you hope to finish this year?
So the team reliably tell me, and I'll take them at face value, they're going for at least top 3.
Oh, right, okay, fine. So there's
Bold claims.
yeah, a lot of space for disappointment.
But I will support them in that.
Right. So moving on to our next talk, this is going to be given by Dr. Felix Leach. So he is a tutorial fellow in Keble College in the department. He is a fellow of the Institute of Mechanical Engineers. His interests are in thermal propulsive systems, air quality and noise pollution, a particular focus on clean combustion and clean emissions. So he's going to be talking to us about transport sustainability, where are we going and how do we get there. So Felix.
Richard, thank you very much for your introduction. It's great to be here to talk to you this evening. I wanted to start by making an observation. These two cars on the screen are the same car, but very clearly they are not the same car. They may both be Fiat 500s, but the vehicle that you're actually getting if you buy a Fiat 500 from the 1980s or from the 2020s is a completely different car. And this is a trend we see absolutely everywhere. And it's not just this anecdotal trend. The data really backs it up as well. No matter where you look in the world, our cars are getting heavier and heavier. Now, of course, some countries are famous for their bigger, heavier cars. You know, the USA springs to mind immediately. Others, such as Japan, are famous for their small cars. But wherever you are in the world, cars are getting heavier. And what I want to do over the next 15 minutes or so is talk to you about why I think that's a bad trend and what we can do about reversing it. But today's also not just about cars, it's about motorsport. So you can see the same trend happening in motorsport series. So here we've got the vehicle minimum weights from Formula One over the last 120 or so years. Forgive me for any experts in the audience. Some of the data from the first half of the 20th century, it's quite hard to deconflict whether it includes driver weight or not, so there's probably 70 or 80 kilos in some of these earlier numbers. But you can see the first cars, such as top left, that's a Mercedes from the 1910s. Big car, 2 drivers. They're quite heavy. And over the following 50 years, cars got smaller and smaller and lighter and lighter. So see the Ferrari in the middle from the 60s, very small, very lightweight racing cars. Since then, we've crept up and crept up. And the current regulation set are one of the few in the last 50 years where there's been a reduction in vehicle weight. Almost every other regulation set has seen an increase in weight, Formula One. But that's not just true of Formula One, it's true of pretty much every motorsport series. So pick your favorite motorsport series. Almost all of them have seen pretty substantial increases in vehicle minimum weights over the last 30, 40 years. So why has this happened? And actually, thinking about this through a motorsport lens is a perfect analogue for why this is happening in the automotive world as well. The primary reason is safety. Vehicles have got a lot safer. Crash structures, the halo in F1. You see the image on the top right of the screen. That's Zhou Guanyu's crash at Silverstone a few years ago. He walked away from that car. That's incredible. That, of course, comes at the price of some weight, but I think we all agree that's a price we're willing to pay for that immense safety. Refueling's been banned in Formula One, so fuel weights have gone up. We're seeing power units such as batteries, hybrid technology, that adds weight as well. And also the cars are just bigger. And that's useful for a number of reasons, for vehicle dynamics, but also for the aerodynamic platform. That adds a benefit. But that benefit comes at a cost, and I think that's been a bit of a hidden cost over the past 40 or 50 years. The other reason we have heavier cars is people like bigger and heavier cars. So this is data from the USA, but it's representative of the world. And what I would have considered a car made up about 80% of the US car sales in the 1970s. Today, it's sub 30%. And some big brands, such as Ford, don't make traditional cars anymore. They make SUVs, they make pickup trucks, and they don't really make cars. So us, as consumers, have been driving this push towards bigger cars because it's what we want, what we demand. But these things have come at a cost. And I got started on this by looking at this vehicle. And I just thought, intuitively, this car cannot be an environmental benefit. But it is badged and sold, at least in California, as a zero-emissions vehicle. And it comes with government subsidies because of that. You can't buy it in the UK, so that doesn't apply to the UK. But intuitively, this can't be the solution to our transport sustainability. So I want then to pose a thought experiment to you all. We know that cars are getting heavier, and I'm going to assume a sort of goodwill from the consumer, that people want to do the right thing. Clearly, there'll be some edge cases where that's not true, but in general, that's true. So let's ask the question. If you could know only one single piece of information about the total environmental impact of your vehicle, what would it be? Now, of course, given where my talk has started, the answer is perhaps before the question. But nevertheless, it's worth exploring it. And I think we also need to ask ourselves the question, is this even possible? Because clearly you cannot create some sort of rating or index system to balance everything, right? There are too many variables, and it's about what you would prioritize. Do you care about the CO2 emissions from your vehicle? How do you use your vehicle? There are so many variables, it's impossible. However, is there something that's good enough? So, to skip ahead to the answer is clearly mass. And if you want me to sort of show my working, come and ask me afterwards, because I could bore for Britain on the subject. But I think if we know that the answer is mass, we can sort of think about it at a very school level. We know that work done is force times distance. I think there's an analogue for us to explore here, which is that the environmental impact of our vehicles is going to be the mass of that vehicle, its weight, multiplied by the annual distance that you drive it. So let's just give this a little test. So with my colleague Nick Molden, who's another Oxford graduate who works for emissions analytics now, we tested just over 1,000 vehicles. These are internal combustion engine vehicles, so hybrids, petrols, diesels, all that sort of thing. Looked at their weight and looked at their CO2 emissions. These are real-world CO2 emissions, not from test cycles or anything. And you can see that while there's huge variability in classes, driven by whether or not they're hybrids and things like that, there is a strong trend that the heavier the vehicle, so the right-hand end of the graph, the higher the CO2 emissions. But it's not just true of internal combustion engine vehicles. It's also true of electric cars. This is some data looking at energy consumption from a wide variety of electric vehicles, and perhaps unsurprisingly, the sort of e-bikes and scooters have incredibly low energy consumption and low weight. But once you kind of move out of that category into things that you might reasonably call a car, you've got quite a nice linear trend between the mass of that vehicle and its energy consumption. That's not necessarily surprising, but it just validates the argument that as we use a vehicle, its energy consumption is going to go up with its weight. But also, if you think about it, that's also going to be true of the life cycle impact of that vehicle. Of course, there'll be differences between classes of vehicle, but as you increase the amount of stuff that goes into a vehicle, the emissions associated with that amount of stuff are also going to go up. Now, we talked about safety in F1. What about safety in vehicles? And here's where you kind of get a real diverging set of outcomes. If you are in a heavy vehicle, that's very good for you from a safety perspective. If you are hit by a heavy vehicle, that's pretty bad for you. So it's a classic example of an externality that what's good for you is bad for everyone else. And these two graphs illustrate that. So the graph on the left shows the risk to the driver with the mass of the vehicle that you're in an accident, and you can see the decreasing trend. The one on the right shows the relative risk of mortality against the mass ratio of two vehicles hitting each other. So if the mass ratio is 2 on the x-axis, that means the vehicle that hits you is double the weight of your vehicle. And you can see that if the vehicle that hits you is around double the weight of your vehicle, your chance of dying in that crash is about 10 times higher. So it's a really, really classic externality. And so the logical thing for me to do then is, if I'm buying my next car, I need to buy this. It will be incredibly safe. Not so sure about the fuel economy on this, though. So moving beyond safety, let's think about infrastructure. Potholes are the bane of everybody's life. It's the day of the local elections, and potholes have been flying through my letterbox with alarming regularity in the recent weeks. The thing is, potholes aren't an abstract thing. They're caused by vehicles driving over roads. The heavier the vehicle, particularly the axle weight, the more likely a pothole is. Our vehicles have got heavier. That is clearly a reason why we're experiencing more potholes. Similarly, this is Hammersmith Bridge in West London. It's been closed for 7 years. I'm sure the local elections around there are dominated by this topic. One of the reasons it's shut is because this was a bridge designed in the late Victorian times for horses and carts. We've now got incredibly heavy cars going over it. Our infrastructure isn't built for these heavy cars. Our potholes, our roads. This photo on the left is from St Aldate's. You can see that that bus stop, big heavy buses turning their wheels, has been resurfaced 4 times. And finally, do you struggle to find a parking space? Do you struggle to fit your car down your road? Again, the standard width of a British road is 7.5 metres. In the late 19th century, that was enough to park a car on both sides and drive 2 cars down the middle of the road. Today, if there are 2 parked cars on either side of the road, you struggle to fit a single car down the road. Our infrastructure is not built for these cars either. And finally, I remember playing with Lego when I was a kid. Lego looked like it did on the left. We have become so culturally inculcated with bigger, heavier vehicles that Lego has had to get wider. It's seeped through the whole of society to accept bigger, heavier vehicles. And I think there are very, very good engineering reasons that I hope I'm demonstrating why that has to change. And here's why today is a great time to fix this. So, vehicles are electrifying, right? We've got amazing battery electric vehicles coming onto our roads today. The UK fleet is rapidly changing. This means we're using less petrol. However, for a government, that's a bit alarming because it means they're taking less revenue in petrol tax. You may think of that as a good thing, but I can assure you that governments don't think of that as a good thing. So, and indeed, petrol duty has actually been, the revenue from it has been falling in real terms since the middle of the last decade. So here's an idea. Let's get rid of road tax and petrol tax. Cheers around the room. However, on a revenue-neutral basis, let's replace it with a mass times distance charge. Immediately, you can start to shift the basis for our taxation onto a parameter which, okay, it's not perfect, but is a really good surrogate for the environmental impact of our vehicles. And in fact, if you think about the 3p per mile EV charge that's come in, that's about what you would expect if you're going to start to phase this in with the proportion of battery electric vehicles in the fleet over the next 20 or 30 years. So I think things are heading in the right direction. So let's just run it as a little calculation. So to work this out, I think you need these 4 parameters. You need to know the average mass of a vehicle in the UK. You need to know the average annual distance that it's driven, the total number of vehicles in the UK, and the tax revenue. So last year, we raised about 40 billion in taxes on vehicles. So you can work it out. You can say that the annual tax will be the mass of your car divided by the average distance you drive divided by the average, times by the total tax revenue raised divided by the number of vehicles taxed. So I just put together some examples from kind of common vehicles you've got in the UK with a kind of indicative mileage that you might drive. And the tax under the existing system is a combination of the annual tax. So this doesn't include the higher tax you typically pay in the first year where you acquire the vehicle. And hopefully in this table you can find something that might approximate the car that you drive and the distance that you travel. And you can see there are winners and losers. The ones I'd particularly like to highlight are if you have a heavy car and you drive it a long way, like a Tesla Model Y, you're going to start to be paying quite a lot more tax. If you have a sports car, like a McLaren 720S, and you don't drive it very far, you're a big winner. And that's going to be a big change, right? Because that's perceived as a luxury. And maybe, we shouldn't politically accept that. But the environmental impact of that vehicle, not driven very much, is low. And so should it be taxed highly? That's a question for politicians rather than engineers. But that's how this shakes out. So to conclude this bit of my talk, I think I can argue that vehicle mass is the single best predictor for the environmental impact of vehicles. And now we're in this diverse powertrain world where emissions are no longer linked just simply to putting the petrol or diesel in your car. We need to move on and we need to update our taxation system to account for this so that we can start to wind back the really damaging trend from the last 15 years or so of heavier vehicles. And I think good enough, rather unattainable perfection is what we should aim for. But in the last 5 minutes or so, what I'd like to talk about is two fantastic undergraduate student projects that are linked to this area, but not directly linked to vehicle weight. So the first is a project from a student last year, Will. Many of you will know that in Oxford we've been lucky enough to see about 160 battery electric buses deployed on the roads. Many of you will have ridden on them at a cost of about £82.5 million. And these buses don't do some of the long distance trips, to London or the airports or whatever. They're what we call the Oxford Smart Zone. So they go out to places like Kidlington, but they don't go as far as Abingdon to kind of calibrate where these vehicles go. And what this project was interested in as part of a bigger project was what the noise pollution implications of these buses were and also what the air pollution was. And Will's part of the project in particular measured the noise using, he brought a prop, one of these devices. So these are called audio moths. They're a spin-out from computer science department here at Oxford. And these are noise pollution instruments. You can leave them on lampposts. They run on 3A batteries. Fantastic for something like a 4YP. And so here's what Will found. We measured the noise from before when the buses were deployed and then after at a number of locations in Oxford, you can see on the map, many of which are sort of what you could call along the central bus corridor for running from St Aldate's down to the Plain roundabout, where there's a very high level of bus traffic and relatively few cars, and then some control locations in Oxford where there are no buses. But still cars and other things that affect noise, right? Such as wind, rain, all these other things that affect the noise profile. And what Will found was that depending on what location we measured, there was an average 5 decibel decrease in urban noise, whereas at the control locations, for whatever reason, particularly weather dependent though, there was around a 7 decibel increase. Another part of the project also found there was a 24% reduction in nitrogen dioxide at bus locations. So this change from diesel buses to battery electric buses has led to these noise and these air quality improvements in Oxford. And of course, you can also strap these audio moth devices to the buses themselves. And you can find that when the vehicles are off, perhaps to my relief, the sound profiles are very, very similar. But when the vehicles are on and running, the electric bus is sort of 20-ish decibels quieter than the than the diesel bus. So fantastic set of improvements for the sort of Oxford urban soundscape. The last one I wanted to choose to highlight to you today is life cycle analysis. So this is a project from Alfie. And there are different approaches to life cycle analysis. This is particularly when applied to electric vehicle charging. You could take an average of the grid intensity. You can sometimes use marginal. People who want to sort of give negative views on carbon emissions can do that. But today we have data. You can go and find out what the carbon emissions from the electricity grid are today, right now in Oxford, online. And so there's the link to do it yourself. This is just a screenshot I took a couple of days ago. And we use a statistical method to say, if I plug my EV, or indeed my phone in right now, here is how much the carbon emissions from that action are. And then we can work it out for all of Europe. So this is the work that Alfie did. And you can sort of strum up some scenarios. But the message is that across Europe, it is almost always favourable, unless you live in some far eastern countries, so Poland, Czech Republic, and so on, to switch from a battery electric to a battery electric vehicle. However, in some cases, that change is quite marginal. It's of order a few light bulbs, rather than a massive improvement in some countries. But if you live in the Nordic countries, it's a fantastic improvement. And this project won an international ASME prize as well. So congratulations to Alfie for that. So I'd like to conclude by just acknowledging Will and Alfie on the left, Nick, Pat, who's a visiting fellow, Martin, who's in the room today, Tristan and Kelly, a visiting professor, all the people who've collaborated on these projects today. And of course, I've written some books on this subject, which you can buy in all good bookshops. And I'd be very happy to take your questions. Thank you very much for your attention.
Good evening, everyone. Hello and welcome. It's fantastic to see so many people here and such a wide range of faces, some of whom I recognise and some of you I'm seeing for the first time. And I'm really delighted that we've got such a good audience here for this talk. You'll have seen that this talk is called the Maurice Lubbock Memorial Lecture. And so before I introduce the speaker, I'd like to invite Lord Avebury, who is the chair of the Lubbock board, to say a few words about this.
Thank you very much. Maurice Lubbock was my grandfather. He would have been very interested in tonight's topic because he started life as a director of Rolls-Royce before moving into more management positions, which is what gave birth to the Lubbock Trust after his death. As well as being involved with Rolls-Royce as one of its directors in its early days, I'm afraid to say the sort of flip side of that, he was a multiple speeding offender. And so he would have enjoyed the speed in the title of one of the talks today. My family have a bit of a history with motorsport in general. After my grandfather, the third Lord Avebury, actually was very interested in motorsport himself. He built, in 1937, a car called the Lammas Graham. It was a bit of a vanity project, white elephant, but nevertheless it was quite a feat of engineering, and he mostly sold it to his friends before the company had to give up the ghost a couple of years later. But they are a historical curiosity, and if you're interested in vintage cars, it's quite a rather sleek design for that era. He also went into production with this for a couple of years, so I'm sure he would have been interested in this topic as well. Anyway, the idea of these lectures is, and I'm pleased to see by the variety of the audience today, is to improve the appeal and the audience for engineering and associated management of such. And I think, if today's anything to go by, and we are actually streaming this as well, so there's another audience like this on over the airwaves who are watching it. Hopefully it's beginning to achieve some of that sort of objective. So I'm very interested to hear what our speaker is going to have to say today, and I shall enjoy catching up with him afterwards, as I'm sure many of you will do. So enjoy your lecture. Thank you.
So we're very fortunate today that John Owen has agreed to come and give this talk. John Owen completed a degree in aeronautical engineering and a PhD in aerodynamics at Imperial College before entering the world of motorsport in 2001. He started his career in Brackley as an aerodynamicist for chassis manufacturer Reynard Motorsport. A year later, he moved to Hinwil in Switzerland to work for the Sauber Petronas F1 team, where, as senior aerodynamicist, he led the aerodynamic development of their new cars and continued as the team transformed into the Works BMW team in 2006. At the end of 2007, John returned to Brackley as principal aerodynamicist for Honda Racing, and then led the aerodynamic development for what would become the Braun GP BGP 001, which won both the Drivers' and Constructors' Championships in 2009. In 2010, John was promoted to Chief Designer for the Mercedes Works team. He led the design team at Mercedes to 7 Drivers' Championships and 8 Constructors' Championships. During his time at Braun and Mercedes, he was central to original concepts including double diffusers, FRIC suspension systems, front-rear interconnect, double DRS drag reduction systems, and dual-axis steering. And so I'm delighted to have John here today to give his talk titled Formula One Car Design, the Good, the Bad, and the Ugly.
Okay. Right, good afternoon, everybody. I'm just trying to work out what the microphone level is. I think we've established that. Thank you very much for having me over. This is a great honour. I've been told by former Oxford students how sort of instrumental this was when they would come along and get the chance to come to the Lubbock Lecture, and I'm really honoured to be here today. Formula One is a very big subject. There's a lot we could talk about today, but what I would like to talk about is, let's say, I want to talk about a few things relating to how we do our cars when they go good, when they go bad, when they go ugly. And so, to take you through the talk, we're going to talk a little bit about the history of Mercedes and Formula One. We're going to talk about the cars. We're going to talk about what makes cars that are good. We talk about the margins between success and failure. We've got the good, the bad, and the ugly. You'll be like, there is no music, unfortunately. But and then we've got the importance of engineering judgment. And I think that's the key point I want to finish on today, which for people in technical environments is the difficult part in all of our lives as technical people. So, for those of you who don't know much about Formula One, I suspect most people do, which is why they've come to the talk. But if you didn't, Formula One World Championship has been around for quite a while. It's hosted around the world at typically 24 races. You'd have 11 teams, 22 drivers, and it's split up into a couple of practice sessions on a Friday. Saturday we'll do qualifying and a practice, and then the races on Sunday. For 2 hours, 305 kilometers minimum. And this year we've got 24 races. Unfortunately, as we can understand why, 2 races in the Middle East got cancelled, and so far we've completed 4 races of this season. If we go on to talk about the team a little bit, so as mentioned in some of the earlier talks about Mercedes got mentioned, I think in both of the talks, and Mercedes has been around for quite a while, but realistically I want to talk about when they entered Formula One for the first time in the post-war era in 1954. They entered halfway through the season, and despite entering halfway through the season, still won the championship that year at their first attempt. And here is Juan Fangio in the W196, a car that I've been privileged enough to sit in, actually. It's an amazing machine. I'm not sure I'd have ever wanted to drive it at the speeds he did. But this was an amazing start for Mercedes in Formula One. In 1954, they came back and won it again. But then they left. And the reason they left is rather sort of unfortunate, because in 1955 in Le Mans in France, there was a very serious accident in motorsport. We were just first in this Formula One era post-war. Safety standards were not what they used to be, and one of the cars entered the crowd, and it was a Mercedes, and as a result of that, Mercedes decided they would suspend their involvement in Formula One. They didn't come back. They had plenty of time off. They didn't come back until 2010. They were involved supplying engines from time to time, but realistically, they first came back in 2010. So, when they came back, they bought a team, and the team they bought was the Brackley team, as we call it, which originally started life as the British-American Racing Team back in 1999. That team went on, didn't amount to very much, struggled along. I think they boldly said they'd win their first race. They didn't. I don't think they scored a single point in the first year. So they started with high ambitions, but quite a big reality check. They were purchased in 2005 by Honda, and they became the Honda Racing Team. And again, they sort of limped to one race win during their time as Honda. And eventually Honda decided at the end of 2008 they'd had enough. They were going to pull out of Formula One. The team was going to basically be closed down, and that would be the end of the team. But a few brave souls struggled on across that winter, fitted a new engine to the car, managed to get some funding, and the team that would enter that championship that year was the Brawn GP team. And that team, despite having looked like it would never actually compete, went on to win the Formula One championship for both the driver and constructor in 2009. And you certainly learn about teamwork and who your teammates are when in the, let's say, November, you're told you're not entering. And in that period before the first race in March, you've got to actually completely reinvent the entire car and organisation. As a result of that, Mercedes thought these guys are probably worth a bit of a punt. We'll invest in them, we'll buy the team, and Mercedes, who've been supplying us the engine for 2009, bought the team and entered Formula One full-time. Our site is based up in Brackley, which is not far away from here. It's just over the border in Northamptonshire, and we have plenty of facilities there, wind tunnels, engine dynos, aero departments, manufacturing facilities. We've got a restaurant and a gym, which is pretty good. It's not open yet, but that particular one, but it will be shortly, so I'm told. The standing joke in our place, if you're driving by, is it looks like the Premier Inn, but don't come in and try and stay there because it's not open to the general public. On site, in the technical area, we've got 4 main departments. We've got the aerodynamics department, we've got vehicle dynamics and simulation, we've got design engineering, and we've got the race team. And if we look at the makeup of the team, it's broadly split up into that many people. So lots of people on the operations side, operations and manufacturing, they make the components, they make the parts, they make the cars themselves, they machine those parts, they laminate the carbon fiber. Also operationally, they're organising the shipment of those cars around the world. To go to 24 races around the world requires a massive logistical challenge, and that is taken on by our logistics team. In the middle, we've got the technical team. I'm part of the technical team, and they are the people that invent the car and do the technology of the cars. And they make up those 4 technical departments I mentioned previously. And finally, on the right-hand side, we've got the business support. Formula One is very good at consuming large amounts of money, and that area is very important for pouring that money into the team, which we can use to develop. At the bottom, it's also worth putting in that we actually have quite a lot of young people, so people that Ryan's talking about in the Formula student team, people coming in doing industrial placements for 12 months, which is a great opportunity. Maybe 40 people a year come through our team, and they get that chance before going back to university to really see what's involved. If you watch Formula One, you'll have seen about that much of our team. Those are the people you get to see on the telly. A few people from business support, a few people from the technical team. That's all you get to see. And there is a massive amount of people working tirelessly behind the scenes that you don't ever get to see. So let's talk about our Formula One cars first of all. And so I've been at the team a while, as it's mentioned, since 2010. And since 2010, we have made all these cars and raced all these cars. There's some good ones in there that people may remember. I mean, if I step forward so I can see them. Some have won championships, some have not. Some we liked, some we didn't. So when we look at these cars, how are we really going to sort of, rate them? How would we sort of say, stood here, what are the good cars? Well, I guess why we're in Formula One. We're in Formula One to win. So we could say, well, which ones of these won championships? So we can put them into championship order. But before we do, this one's still competing. So we can't judge this one yet because it hasn't finished the season. So we need to get rid of that guy. And we can take the remaining ones and we can say, okay, so how would they arrange if we put them into championship order? And if we shuffle up the cards, we can see that those were first, those were second, those were third, fourth, and fifth. And that looks pretty respectable, doesn't it? I mean, that's sort of reasonable. We've done quite a lot of wins. We've done quite a lot of second places. We've got the solitary third. And then we've got these ones on the right that we're trying to forget about and we feel are not as good as the others. Okay, but there's a problem with this. If we just take the finishing order of these cars and we say, well, this is a good one, this is a bad one, it's not really true because think about what we're judging when we say that. It's what we get paid for, it's what the intent of the team is, but what is there? Well, some of these things, obviously, are, our performance and our finishing position is affected by other things. There's our old favourite, driver error. We have a saying, ambition over adhesion, and there's an example of that. Pit stops, things go wrong. We're trying to change our wheels and tyres in 2 seconds. We can get things wrong. Race strategy. Everybody thinks they can do a great race strategy, and every now and then they don't. We've got the weather. We stay out. We think we keep running around. It's not going to rain. It's not going to rain. Oh, it rains. We have unfortunate bad luck. You can be minding your own business and someone arrives upside down and runs into you. And perhaps the most crucial thing when we try and judge ourselves and where we can't use championship performance is how good your competitors are. Because if your competitors are not good, you look amazing. And if your competitors are amazing, you look terrible. So your competition really defines in a championship how good you finish. But it doesn't really tell you what is a good car and what is not a good car. So it's not a reliable metric, really, to determine what our best cars are. So how are we going to do better? Well, it turns out the technical team are pretty good at judging whether they've made a good car. If you ask them, they can say, well, has the development rate been strong? No obvious deficiencies in the car. It responds well to its setup changes. It's gentle on its tyres. No missed innovations, because we release our car, we bring it to the first race. Have we missed some crazy wing that the other guys have got that we haven't got? Should we have had 6 wheels and they've got 6 and we haven't? Or have they got some winglet behind their exhaust we hadn't got? And all the other things do. They have double diffusers. Have you got all the right innovations? And if you haven't missed anything, you think, okay, well, that's good. We're in with a chance. Drivers drive it. Do they like it? If the drivers like it, that's generally a good sign. And then finally, the most important one, is it actually fast? So if we take all those things, we can start to judge whether we've got a good car. But the important thing to remember is that as a technical team, we might think the car's no good at all, but it can still be winning races. So let's go through that again then. And this time, let's put them into sort of a pocket and sort these out of how we would rate them. Now, we can keep the current car in because it's racing, and we can rate them differently. And we can rate them as the good, the bad, and the ugly. And if we look at these cars and you followed Formula One, you might be surprised to see where some of them are. So if we start in the top left of the good, the car, up there's the 2013 car, W04. Second place in the World Championship, but it's in good, didn't even win. What's it doing there? Also in good are, well, 6 of them are championship winners in that category. And the bottom right car, the one we're racing at the moment, we've also decided to call good, even though it's not actually finished the championship yet. If we look in bad, perhaps the bigger surprise in there is that sort of second one down is the 2014 car. That car dominated Formula One in 2014, the W05. People talk about that car as it being incredible. I looked at that car for the whole season and thought, God, when are the other guys going to come and catch us? Because I'm feeling quite vulnerable to the fact this car's not very good. Luckily, nobody came, and it was a bit of a cakewalk, the whole thing. But we were fortunate that year to not have strong competition and to have a very strong engine in that car. But it wasn't a great car. Equally, 2017 won the World Championship, started life, had a very difficult birth, that car. And I think by this time in 2017, I think I'd already spent £15 million on trying to sort it out. So some of these cars are not born great, and they're a bit difficult. And if we come to the far side here, we've got the ugly cars. Well, the 2010 car sort of just came into being. Nobody really invented it. It was just a collection of bits. The 2012 car was actually a backward step in a number of ways. It did actually win the first race for Mercedes since they entered Formula One. It wasn't a good car. And then the final two on the right-hand side are our famed 2022 car on that car, which we'll be talking a bit about later. And it's next generation, the 23. Okay, so what we often get asked is, well, how can things go from being good to not good, or even ugly? You know, to the non-expert observer, you know, you're always winning. It's kind of business as usual, isn't it? You know, why wouldn't you just keep winning? You know, it seems completely inconceivable that you could go from winning in Formula One with the same group of people and then next year make something that's really quite terrible. But it's not a surprise to the people who run the technical side of Formula One and work in the technical side, because we know that the margins between success and failure are very, very fine. We know that we're always under pressure to push what's possible with these designs, but if we get it wrong, we end up in a big mess. So, people often tell us this, mainly the people that we work for. Why can't we just make good cars? You're smart. Why not? But it's difficult. And you could take the parallels, which is We see our drivers in the qualifying sessions driving right to the limit of what these cars are capable of doing. And sometimes they crash. And we could say, well, why have you crashed? You're the best driver in the world, Lewis Hamilton. You were the world. Why have you crashed your car? I thought you were good. Well, they crash because they're trying hard. And in Formula One, when you try hard and you try too hard, you end up with a bit of a mess. And we're going to talk a bit more about that. So let's first of all skip through a few things about what makes a good F1 car. That will help us understand the ones that we're going to come back to. So you really need two things. What we're going to call base performance, strong base performance. This is kind of the raw forces, engine powers, downforce, grip, things like that. And with those forces, you need excellent handling balance. This is how much of that kind of forcing and acceleration you're creating from the car that the driver can actually have access to. You can have cars with lots of grip, but they're not very drivable. And it's probably captured best in this sort of contour plot that I put on the screen. So let me explain the plot a little bit. We've got contours of lap time. And if you look at the top there, you've got 85 seconds, 84 seconds, 83 seconds, and it's getting quicker. And if you look on the x-axis, we've got handling balance, and on the vertical axis, we've got base performance. And you can see that if you go up, increasing base performance, you start crossing those contours that gives you more performance, and you go faster. And you can also see that if you cross, you can go to the right, and you can cross those contours and increase performance. So as we increase the handling balance, we increase the amount the driver can extract, we can go faster. And if we increase the basic performance of the vehicle, we can go faster. But you can also see that it's very easy to trade one for the other, doing lots of work, making your performance, your base performance better, but your handling worse, and you just end up not improving your vehicle. So let's talk about what's in base performance. Well, it's said that a Formula One car should never be moving at constant velocity, but always accelerating. And if you look at a plot of Silverstone, we've got a speed trace on the right-hand side there, kilometers an hour on the vertical axis, and just basically distance. And you can see, as you look at that, the car speed is changing dramatically. Now, you might say, well, yeah, but it's sort of almost constant speed in that first bit. This is true, but remember, we're talking about moving at constant velocity. And being a vector quantity, the car is maybe moving at constant sort of speed, but it's accelerating very strongly laterally. And where that first peak is, by 300 kilometers an hour, the car will be experiencing about 5 lateral G as it goes through the first corner at Silverstone. So it is always accelerating in a particular direction, and we don't want constant velocity. Well, we know from our kind of schoolbook physics that if we want to increase our accelerations, we're linked by force and mass. Make your forces big, make your masses small. Masses, unfortunately, in Formula One, we talked about that in the previous slide, they have come down a bit, but we have a minimum weight for safety reasons. We're not allowed to make the car lighter in the current season, 772 kilograms. And once you've reached that, the lower term in that equation is no longer available to you. You have to concentrate on just improving forces. So if we look at the dominant forces in a race car, the main forces we're dealing with, tire forces, there are forces that connect us to the ground. When the vehicle tries to corner, it's those forces that are actually turning the vehicle. Equally, it's those forces that are accelerating and braking the vehicle. So in the longitudinal sense, we've got propulsion, we've got braking, and we've got aerodynamic drag. We've got lateral forces, which are the things that provide cornering. And again, if we think about the car, it's moving really in a two-dimensional sense. We're only really interested in lateral and longitudinal forces in terms of setting lap times. But of course, people who follow Formula 1 will know we do quite a lot with aerodynamics. And so vertical forces are important, and vertical forces are important because we're trying to increase the normal reaction force off the ground from the tires. We're trying to push the tires harder into the ground, and the harder we push those tires, the more lateral forces and longitudinal forces we can generate. So we have weight, but we use aerodynamics. And often people talk about aero, and they sort of think, well, what downforce have you got, and what does it mean? And they talk about points or other things of downforce. But I think this plot here is probably the easiest way to sort of show you what aerodynamics does to a Formula 1 car. So horizontal axis starts at 60 kilometers an hour, and it moves upward to 300. And you can see at the bottom, there's just a big chunk of weight. On the vertical axis, we've got the reaction force on all 4 tires in sort of kilonewtons. So we've got about 1 kilonewton at 60 kilometers an hour, Most of it is the dead weight of the vehicle, what we like to joke about as static downforce. When we're overweight, we say we've increased our static downforce, and that's generally not a complimentary statement to be making. What you can see, though, is that as the speed comes up, quadratically the aerodynamic forces are increasing. So very, very quickly, by the time you're up to sort of the 200 kilometre an hour range, you've already got 3 kilonewtons of force. You've got another 2 tons on there. So we talked in the previous talk about heavy vehicles, and they're not good. These vehicles are quite light, but they've got the equivalent of maybe a Tesla Model Y dropped on top of them at decent cornering speeds, pushing them into the track surface, generating the grip. So what we like in Formula One is, well, okay, we've got all these forces. How do we need to change them to make ourselves go faster? Where do we put our effort? So we could increase the tyre grip by 3%. Now, the tyres are standard, but we can find ways to make them better or worse. They get hot, they lose grip, generally. They get cold, they lose grip, and there's a sweet spot. So if we can maximize the grip of the tyre, we can find about a second of performance, which would take you from the back of the grid all the way to the front of the grid last season, if you could get 3% more grip. We could reduce the mass if we were overweight. 4% mass reduction, 1 second. We could increase the engine power, 7% of engine power, another second. We can increase the downforce, 10%, and people say, well, why 10% that and 3% grip? Well, if you look at the top plot, you can see that the aerodynamic forces, when you increase them by 10%, they don't do much at low speed. So you need bigger increases. Drag reduction, again, we can reduce the drag of the car, and then we'll spend more time, we'll accelerate faster, less time on the straights. So how do we develop base performance? Well, first thing we do is go in the wind tunnel. We've got a 6% wind tunnel. There's a model from several years ago inside our wind tunnel. We use computational fluid dynamics, but we had large restrictions and regulations. We're only allowed to test 30 different configurations per week, typically. Now, that might sound a lot to some people, but a decade ago, when I was in aerodynamics, we'd be testing 400 per week, running 24 hours a day, 7 days a week. Now, that's restricted for cost reasons, so we only get to do 30 runs per week. So we have to be quite clever about what we do, and that's why we use quite a lot of CFD initially to check our solutions before we put them in the wind tunnel. We develop engine performance. That's a cutaway model of last year's engine. The engine is not made by us in Brackley. It's made by our sister team, or our sister company, High Performance Powertrains, up in Brixworth. And they produce the engines for several of the cars, but primarily for us. And their job is to relentlessly look at thermodynamics, combustion cycles. And that engine pictured there was probably the most thermally efficient engine in the world, despite being a tiny little racing engine. So lots of work goes on up in Brixworth. And then finally, we talked about tyre grip. Lots of work goes into trying to understand how to work with tyres. Now, I could talk for another 4 hours on tyres. I'm not going to, because I'll probably say all the wrong things, for one thing. But the main thing about tyres is they are extremely complicated. And I got asked yesterday at a university visit to Southampton, why don't you have tread on your tyres? Probably one of the biggest misconceptions for a lot of people is they think the grip that you have on your shoes, seemingly, or the kind of tread in your tyres is what makes grip. That's just to clear water when it's wet. If it would only ever dry in this country, you wouldn't want any tread on your tyres whatsoever. You just want slick tyres. So I'm not going to talk more about it because we'll be here all night. But tyres, ask me later if you've got an interest in tyres, and I'll bore you later. So if you put all this development together, and you keep on developing and developing and developing, you end up with a tracker. And in Formula One, we love a good tracker. We like to see how we're doing. It's trying to keep our heads up. It's trying to keep us positive to see all the gains we're making or not. And that track on the right-hand side, sorry if it's a bit too small, is just weak numbers on the bottom, and the green line is just basically our performance going up. And that little red dotted line is where we think we need to get to if we're going to be good enough. And strangely, that one was for a car that turned out to not be good enough for other reasons, which we'll come on to later. Okay, so handling balance. Road cars and the way you normally drive them, if you're a sensible person, are very stable. You never think of things as being unstable. You let go of the steering wheel, it straightens up. The car wants to run straight. It wants to drive straight. It's an inherently stable car in a 2D plane. But if you get involved in race cars, you're driving them well beyond the grip limit of the tyres, and now you need to think about what balance means. So if we look at static balance, this is where our cornering force is. If we just imagine one big cornering force, where is that relative to the centre of gravity of the car? If it goes through the centre of gravity, broadly speaking, we can say we have a neutral balance. Our car will just slide sideways, all four wheels. That'd be probably quite nice. If that cornering resultant force is behind the centre of gravity, and if you look in the image on the top left, you can see we've got a lot of force pushing on the rear wheels and not much on the front, we tend to get an understeer balance. We're struggling to turn the vehicle. We've got plenty of rear grip, we don't have enough front grip. And every road car in the world is set up to be like that, because from a driver's point of view, it's an inherently stable setup. If you try and corner too quickly, the front will just sort of slide out and you'll lose speed. What makes it fun, though, is an oversteer balance, and that's much more fun. And that's when, obviously, the grip force on the front axle is much stronger than on the rear. So we are always trying to set the car up to balance it in corners, and there's a number of things we can do for tuning the balance. I could talk again a lot about these things, but we can actually move where the centre of mass of the car is, forward and backward, within a small amount of range. We can tune the grip of the tyre balance. We have things like where we set the toe of the tyres, with the camber of the tyres, pressures of tyres, temperatures of tyres, so things that can affect how much grip we get from each axle. Mechanical balance is a term I suspect most people are not familiar with, but it's, if you imagine the car is rolling, the reason it doesn't roll over forever is it's resisted by springs. If we make the rolling moment of the car resisted all on the rear axle, we would have a very rearward mechanical balance, and that would then lead to a car that's very oversteery. And if we had all the rolling resistance on the front, the roll moment on the front tyres, that would give us a very understeer balance. And again, road cars tend to have front anti-roll bars and not rear for that very reason, to give you that understeer balance. And then finally, where do we set our wing angles, front and rear, for the aerodynamic platform? Okay, so handling is one of those things that is incredibly complicated. It involves the driver, and there's many things we need to go through. But there's also the side of it, both in statics, there's also dynamic balance. And dynamic balance is the wind blows. And because the wind blows, the center of pressure of the aerodynamics changes. The angle of the car changes relative to the ground. The aerodynamic center of pressure moves. The way the driver slides the car means it gets a sort of an effective slip angle on it. That changes where the center of pressure is acting. So all those things we need to consider in the dynamics of the car. We've got things like the tyre grip, and as talked about tyres being complicated, they are incredibly difficult to work with, the tyres we have in Formula One. You go into a corner with them at one temperature, very quickly they start warming up. As they get hotter, they get more grip, and then very quickly they get less grip. And depending which tyre on which axle, front or rear, gets hotter first, completely dominates the car balance. So tyres are complicated. And again, I mentioned that once already, so we'll move on. We've got mechanical compliance effects. When these cars are cornering at 5 or 6G, the car will bend. The wheels will bend, the suspension bends, everything points not in the direction it was designed to. We have to consider all those things, because all of those things will destabilize our balance. And all of these things we try and model in the driver and loop simulator. Now, that's not our simulator, because I can't show a picture of that, because it's too top secret, but that's just a sort of generic simulator. And the most important mode in that simulator is the yaw response. So that's basically you sitting in the vehicle and your ability to turn and what you feel. It's that yaw acceleration, how connected you feel to the vehicle. And so simulators in Formula One, unlike flight simulators, are all about that rotation around the vertical axis. Then we've got the human limitation. And this is where it gets even more complicated, because now I could talk about within humans, there's actually two parts of a human brain, one that's kind of what we'd call muscle memory, and one that's actually called their conscious thought. I'm not going to go into that, but the division between, let's say, the driver and the car is more about the division between their conscious and unconscious than anything else. The driver's got a response rate of about 4 hertz. That means when the car's going relatively low speed and low speed corners, they can deal with quite a lot of instability. They quite like that instability, the oversteer balance. It helps them turn the car and makes the car feel like more agile. But in the high speed, they can't live with that at all. They're too slow. If the car starts to break away into an oversteer trajectory, the driver won't be able to catch it, and the car will crash. So we have to make sure that in the high speed, we're inherently stable, and in the low speed, we can give the car a bit more instability. Right. Let's talk about how we bring this all together. So we've got lots of technical departments, and we gather all up their ideas and what makes performance, and we try and bring them together. So the competing requirements, an aerodynamicist might want one thing, a mechanical designer might want another thing. How do we bring all these things together into what is going to be a good race car? Well, everybody thinks their bit's the fastest part, and so they should do. They should all focus on, effectively, how do I make this thing the best thing for the aspect I consider? But at some point, we need to take all those ingredients and blend them together. And there's I think it was Boeing that first came up with this cartoon, but this is basically what happens if you let everyone have their own ingredient in the cake. And this is basically what they talked about with how you build aeroplanes. And of course, if you're designing a fuselage, well, there's your ideal aeroplane up there. I particularly like the maintenance group, where they've got a hatch everywhere to get to everything. I think, rather rudely, I think the production one here on the right, that's third one down, is very nice, having a piece of wood with a nail in it to make the wing. That's what they'd like. And of course, you can always see those lovely aerodynamic folk there with the most slender, impossible thing to make that is going to make the world a better place. So you have all these competing things, and somehow you have to turn them into something that looks like what we know and love as a Formula One car. And you have to mix those ingredients together in the right proportions. But as ever, these parameters don't just add and subtract easily. If you've ever cooked a cake and you put your ingredients in, or anything you've made, or any kind of chemistry, reactions and things are not linear, they're quite non-linear. And some of those things, if you get them wrong, have very big effects compared to other things. So it's a difficult thing to get right, to maximize performance in all areas and mix these things together to come up with a good car. So I put uncertainty is everywhere. It is everywhere. Lots of the information you're dealing with is highly uncertain at the time you're having to take decisions. You don't have the luxury to have all of the information at the point you make the decision. So I'm going to give an example. It's a little basic example. Ryan, when he used to work for us, did quite a lot on cooling, as I remember. And we used to have to work out how big to make radiators in a Formula One car. So what's the purpose of radiators? Well, radiators, they cool down lots of liquids we send around the car. They cool engine oil, engine water, hydraulic fluid, gearbox oil, battery coolant. And we have to work out how big to make these things. And in the image on the top right, the kind of silvery bits sticking out the middle of our radiators, and you can see them in the lower image with their air feed ducts. We can basically, we know we have to run these things at the correct temperature for performance. We know that if we run them too hot, it's generally not a good thing. Things fail immediately on race cars if you get them too hot. And we know that cutting big holes in the bodywork is is very painful for our aero team, who desperately don't ever want to do that, because that costs you lots of aerodynamic performance and makes you slower. So you need to work out how you're going to size these things. So let's think about performance factors. We could make them smaller. They'd be lighter. There'd be less metal. There'd be less fluid inside them. We could have smaller side pods. The aerodynamicists would love that. That would probably be something, even though they'd probably end up like they normally do, forcing you to make small side pods and then make them really big, and you have these tiny radiators and big side pods. At least they'd have the chance to go and have a look at it. But as you make them smaller, like anything in aerodynamics, as you make something smaller that you've got to flow a given amount of mass airflow through, it's going to come with higher resistance. So it starts to become quite negative for aerodynamics as well if they go too small. So how do we sort of demonstrate this? Well, what we can do is we can say, well, let's put together a graph, simple graph, which has got performance on the vertical axis and technical risk on the horizontal axis. And as we go bigger, that's going to the right. No, that's going to the left. I'm standing this way. As we make them smaller, we go to the left. And that makes radiators smaller, and we think that might find some performance. But we know if we go too far, it's going to be a problem. So maybe that's our curve. That's what we think. As we go up that curve, making them smaller, we're gaining performance. We're getting better side pods. We're getting a lighter car. We're happy. And somewhere, just before they get too small, and it's really difficult to push the air through them, that's where we want to design. So let's put on our spot, and you think, okay, we're done. That was easy. What's this Formula One business all about? I don't know what you're complaining about. Well, the problem you got is that when we have to decide these things, decide the radiators, lots of things are not clear. So let's do an example. What happens if it turns out the car's underweight? And all the benefits we thought we were gaining from saving weight on the radiators are no longer relevant because we just have to put that mass back as ballast to get to the minimum weight. Well, if we look at our curve now, we can adjust our curve and say, well, it actually ended up looking like that once the car was finished. So we probably didn't really choose the right spot for our decision at all because we'd have been better off putting our cross there. That would have been a better choice. But we didn't know that when we had to make the decision. Equally, we could take another example, and we could say, and this one happens more often than not, which scares us. Our friends who build the engine turn up and say, yeah, it needs a bit more cooling than we originally said. And when that happens, that's a lot more worrying because the curve now moves this way. And now you've got this situation, and that's not good at all. So when you have to judge where to choose these things, it's not straightforward. This is a recoverable situation. We've all done it wrong before. It's generally £500,000 and 4 months to fix it, but it's clearly not something we want to get wrong. And these are the choices that technical folks struggle with that can easily turn into making what was a great car not a very good car. So you've got to be aware how these things might change when you're making your choices. It's not that straightforward, and you can't just pick a graph and say, oh, it's there. Okay. But this is just, one example. So if we look at this, we've got these highly nonlinear interactions. Yeah, it might be that the new bodywork actually now means that the aerodynamic sensitivity to smaller side pods is way more important than it ever was, and we should try a bit differently. It might mean there's no sensitivity to it. These things are continually changing as the design evolves. And, decisions we take, we have to do it with very limited data. And of course, the problem with it is it's not just one decision. They're everywhere. All over the car, you've got to choose these things all the time in very little time. So, loads of little graphs. Some of them have gone wrong, some of them are good, but we have to get them all correct all the time if we want to make a good car. And this is the big challenge we have to deal with. So, this is an easy example, as I keep saying, because it's a very simple thing, because it's just a bit of mass relating to base performance. But when you involve the driver, and you talk about handling balance, and you have to choose out what you're going to do on a suspension, or where you might put the weight, or what your aerodynamic characteristics are going to look like, that work with what the driver can cope with, that is way more complicated. So, I've rambled a bit about what makes good cars. Now we're going to go back to the ones we saw before, and we've already chosen our friends and decided which goes in which pot. But I think in order to sort of understand this a little bit further, what I'm going to do is from each category, I'm going to choose an individual car, which we're going to talk about a bit more. So first of all, the winner is, for the good car, W11. It's our 2020 car. It competed in the year where there was the COVID-19 pandemic. So that year we only had 17 races. It won 13 of them. It got 15 pole positions, and it comfortably won the World Championship. It was a car the drivers loved. We took it to the racetrack. We got it out of the truck. We did virtually nothing to it, and they just drove the car and loved the car. And it's one of those cars we miss. We liked it. It was nice. The bad car is one not from long ago, 2024. This is the W15. It won 4 races out of 24. It finished 4th in the Constructors' Championship, and I'd just call it was a bit of a vanilla car, and we'll come back to why it was bad shortly. And then finally, the ugly car. Well, this is it. This is the W13. It came actually directly after W11. I'll explain that in a second. And it didn't actually do too bad. I mean, it's 3rd in the championship. It's not far behind 2nd. And the reason for that is that year, in 2022, was new regulations, and everybody was terrible. We were terrible, and so was everybody else. And some people were just a little bit less terrible than the others. And hence Red Bull Racing won that year. Our car won one race in Brazil, where it just suddenly seemed to be the fastest car, just at one track. And no one knew why, and neither did we. So that was that car. So let's get into the detail briefly. So I put this plot up to show you a bit about the history of these cars over the years. We've looked at all the different cars we made. But what I've done now is group them into families of solutions where we can talk a little bit about evolution of design versus a revolution of design. So if we start on the left-hand side and we say, back in 2010, the W01, I've colored it as a sort of blue color. It was a sort of a family of cars. We did one of them, and then we immediately came up with a new family of cars. And what I mean by that is we just tore everything up, started again, completely different concepts throughout. And that green sort of family of cars had 3 generations. One of them ended up second place, which was quite good because the rules were quite stable, and eventually we got to a good place. And that set the scene for what we did then in 2014, where we got the new regulations and we won 3 championships in a row. And we did something quite unprecedented then, which is that there was a major rule change, which is normally put in by the governing body to disrupt us from winning, and we managed to continue winning across that change and won another 5 times. In that period of 5 cars that won, I've picked out W11. And the reason I've done that is because W11 was actually sufficiently good that we carried the whole car over with a few new aero parts and ran it again as W12. We gave it a new name, but it was basically the same car. So that is the last real generation of evolution of that family of cars. Then once again, the regulators and the teams throw their hands and they throw the cards in the air to try and have us over, and this time they succeeded. That's when we built W13, and we had to have a new generation of cars. We did 2 to that generation before we said it's not working. We threw it all away and we started again with the W15, and that's why we're going to talk about that one as the bad car. So I'm going to move on, and I have pretty much summarized what I wanted to say in these bullet points, which is quite convenient, speeds us along a bit, and I'm going to move on to the next slide. So, W11, what did we like about it? Well, we'd done 3 already. We were struggling for things to do. We had to start getting more radical with the design. We took on some pretty ambitious projects, and one of those was to do a new rear suspension. And you see there in that image, the rear suspension, the gearbox. There's a very different architecture to how the rear suspension worked. It was quite bold, quite adventurous, quite risky. We did our homework, we worked carefully on it. We unlocked quite a lot of aerodynamic and mechanical performance, and we generally felt pretty pleased with it. We also did a thing called the DAS system, the dual-axis steering system that most people remember this car for. That was just there as a little bit of a cherry on top to try and keep our front tyres hotter. And there was a useful distraction for all the other F1 teams who basically wondered what it did and how it worked. And it was a little bit of fun for us as engineers. And if we compare ourselves to where we were in 2020 against our main competitor, well, that year we were racing Rebel Racing. We were trying to beat them. And we would say that our car was probably better in handling and better in base performance, but much better on the handling side, and it was a very nice car. So, as engineers, we don't like talking about good things, so we're going to move off that one. We're going to talk about bad things. This is the 2024 car. This car is the first of a new generation of cars, a new family of cars. This one we had to create to react to the problems we've been having previously, which we're going to come on to in a second. It was really stable, much more stable than its predecessor. The drivers were much, much happier with it. But the problem with it is we couldn't turn corners, which is quite fundamental in racing. It was okay in the high-speed corners. It didn't like going around low-speed corners. And in a way, what we'd done is we had overreacted to a problem we'd had the previous car. We'd gone too conservative on one aspect of the front suspension in an attempt to try and make the car nicer for the drivers. And we also found out that once we got a car running in a more stable fashion, that the aerodynamic balance, the way it changed around the lap, we hadn't got that right either. So fundamentally, we now started making a car that was a little bit too conservative. We'd taken it, it's like the driver driving a racing lap just a bit too slowly, taking a bit too much margin, taking it a bit too easy. This was a car we made. And fundamentally, we were just underdeveloped. We'd started with the car, reinvented the car, and then 2 years later, we'd started again 2 years later. So we were behind on both handling and performance. And, it's a question of when you go too conservative. And overall, if we put our little kind of ratings at the bottom, those little graphs again, most things were pretty good on this car. But there are a couple of things that weren't, and that just pegged it back from what it could have been. This is the one I want to talk about. And this is the interesting thing, and this is the real sort of where engineering judgment comes in. So this was the first car to the new regulations. We knew we were going to struggle to find performance with these new regulations. So we were sort of predisposed to be quite radical in what we were going to take on. We thought we'd struggle with handling, with the actual raw performance rather than the handling. So we said, let's just work on raw performance first. We thought, let's go maximize that. We won't worry about the handling. We'll sort that out later. Let's go for extreme solutions. And so we did. And we did a lot of technical things on this car, but the drivers weren't happy. When they ran the car, these are the comments they said. and some of you might remember this. It's bouncing like crazy. It doesn't want to go in a straight line. It feels like I'm sitting on the front wheels. You know, I'm driving with my fingertips. I don't feel the rear. The driver said all these things very quickly. These are not things that we really expected. You know, base performance we thought was pretty good. We thought, actually, it's got a lot of grip, but the handling was terrible. And we were lost. You know, generally, we didn't know what to do. And if we move on, and we say, okay, well, what happened? Well, the first thing that happened is this bouncing thing. None of us really predicted this at all. It's a completely new phenomenon that we weren't familiar with in Formula One, at least, let's say, in my generation. People many years ago came across this porpoising. And this is basically a really difficult couple problem that we didn't actually consider, where the aerodynamics, rather than actually damping oscillations in the car, were exciting the oscillations in the car. As the car moved towards the ground, it would gain load as it was moving downwards, and it would lose load as it was moving vertically upwards. So this is an energy input term to the suspension. We also had this sort of output term where we've got to get energy out of this oscillation into the suspension dampers. But Formula One cars run famously little travel in their suspension. The more travel you run in your suspension, remember we talked earlier that we're going to put a Tesla Model Y on top of these cars, so it's got to be quite stiff, otherwise it will just fall on the track. Or you have to start it really, really high up so it squashes down. But you never get much suspension travel and you can't get the energy out. So let's just show you what a car looks like in this bouncing phase. So this is us bouncing along the track. And as you can see, quite a low frequency sort of suspension frequency, about 7 hertz or so, just bang, 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 continuously on the circuit. And the drivers hated it. And all the cars in Formula One had this to an extent. So naturally, you're thinking, something unexpected has happened, all our problems are to do with that. So we thought, right, we'll come up with a new aerodynamic flaw, we'll come up with a new way, we're going to reduce the amount of energy going into the system, we're going to run softer suspension, we're going to have it nailed. So we did that. But when we did that, we were surprised to find out that the handling, if anything, was worse than ever. We went to the Austria Grand Prix, we thought, it's not bouncing anymore, and our 2 drivers went into qualifying, and they did this. Lewis lost the back and crashed, and then a few minutes later, his teammate, George Russell, did exactly the same thing and crashed. They just had no sense of what the back of the car was going to do at all. They just couldn't predict what it was going to do. Rather interestingly, we only had 1 spare floor, and they were both destroyed. To show you the level of teamwork we have in F1, our garage mechanics took the 2 damaged ones, because you'll notice that Lewis crashed one way and George a bit the other, and they cut them in half and stuck one into the other, and next day we went racing. And we didn't race very well because we didn't have a very good car. So we'd largely focused on this problem. This is the silver bullet. We thought, oh, we'll fix this and the car will be great, but it wasn't. And we continued to look into this problem again for more, trying to understand what had gone wrong. And the root of the problem was actually something we'd baked in quite early on. It took nearly 18 months to uncover it, but basically what we'd done is we'd missed a simple thing in the modeling of the rear suspension and how it behaved. And the rear suspension, like many things on this car, was quite radical. And I won't go into the detail of exactly what we'd done, but fundamentally, the rear wheels had a little bit of a mind of their own. If you've ever been to the car apart, to understand where this problem came from. This is what happens when you push the limits of car design, things you want to go for. And once we'd understood it, suddenly everything made sense. There was a very interesting moment where we put George Russell in our simulator in Brackley, and we put the behavior of this into the simulator, and immediately he said, that's what the car feels like. So once we got that, we thought, right, that problem we're trying to solve that we think is the aerodynamics, that problem we're trying to solve that we think might be to do with the engine or the tyres, it's nothing to do with that, it's this. So we could take those problems away, life became quite easier. But unfortunately, at the point where we realised what it was, we'd already committed to keep that rear suspension for the following car, so it blighted another year as well. All the focus had been on something we hadn't expected. We didn't think about the detail of the problem. And so if we look at our score sheet at the bottom, there's plenty of reds, there's plenty of just not good enoughs, and there's only a few things we actually got right. So it's a cascade of consequences. And these are the things I wanted to sort of leave us with a bit today to think about. Those of you that are seasoned engineers, those of you that are going to go out and deal with difficult projects in the future, is think about the cascade of consequences and how they work on a human level. We've had a good car, the 2020 car. It was really good. We took some bold decisions. They worked out well, better than expected. You're sitting on top of the world. You're confident in your tools. You're confident in your abilities. You know things are going to work well. You think we've got to take more chances with a new car. It's new rules. We've got to put everything into it and make sure we get it right. But that overconfidence obviously leads to problems. We ended up on this massive, complicated problem to solve that took ages to get rid of, to understand what had gone wrong. And as a result of that, it knocks into you. It lacks your confidence. You doubt yourself. You're trying to not do things wrong rather than do things right. And when you try and work on trying to not make mistakes rather than just focus on being better, you build things like this where you've got a bit cautious and now it's not good enough either. So it's a real sort of oscillation between the states of overconfidence, catastrophic failure, underconfidence, and bringing it back together. And if we take our sort of shift of it all, while we were doing all that, our competitors just had a lovely time running away from us, which made us look worse and worse and worse and put more and more and more pressure on people. So, the importance of engineering judgment, and the one I want to leave you with really, is that fundamentally in elite sports, the human factors on the technical team are just as important as those on the driver. Positive correlation is but often not more dangerous, let's say, than negative correlation. And what I mean by that, when things go better than expected, you find £10 in the street and you put it in your pocket thinking, oh, it's my lucky day. It's generally not, is it? Because it belongs to somebody else, or maybe it's not going to come. It'll come back around, won't it? And in Formula One, if something works better than expected and you don't understand why that is, sure enough, later on, you're going to be taking the pain of that. Well, what have we got? Good results. Can bring false reassurance. It makes you think everything you're doing is good when there's lots of things you're doing that are bad. Equally, when things go wrong, then you start to doubt your own abilities. You doubt your tools and your own paralysis, and you can't move forward. So the thing I wanted to sort of look at is when you're balancing risk and reward in any kind of thing like this, your judgment is key. And learning about judgment and understanding these things, unfortunately, is not on the syllabus. It's one of those things you have to learn through bitter experience over time, when you have to be pushed to the limit of what you're capable of, but at the same time not make mistakes. And over time, as engineers and as technical folk, we all get better. So to summarize a little bit then, have we learned from our mistakes? Well, luckily, yes, we have. And currently, this is our current car. And we've done 4 races so far, and it's won all of them. And it's going quite well. And we're currently steaming ahead in the Constructors' Championship, and the drivers are happy with the car. We're happy with the way it's responding. And it's quite interesting, the mindset back at the team, because people are looking around thinking, right, what's the crisis to go fix? And there isn't a crisis. We just need to continually improve the car, marginal gains, get back to that calm state of diligent working. So I hope I leave you with a little bit of insight when you've watched this from a distance and think, how does it go from that to that to that, and then back to that? Just a little bit of a look in, because we could have talked about a lot of other things, but this is the hardest part of the job. This is the hardest part as engineers, things that you have to face. If you've got time, people around you to think straight, things are easy. But when the pressure's on and things don't make sense anymore, those of you that have programmed something and the code won't compile, you know that it can take you a very long night to understand what it is. This is what happened to us. I hope there's some useful learnings in there that people can take away for what they do. I'll leave you with any questions.
I think that's all we have time for, although I recognise that a lot of other people have questions, and so hopefully John will be able to talk to a few of you afterwards. The objectives of these lectures are really to promote the understanding of engineering, to promote the relevance of engineering, to promote the role of engineering in the modern world, and to inform and inspire the general public. I think we've had a really good set of talks this evening that have met all of those aims, both collectively and individually, and I'm very grateful to our speakers. I think we want to thank our speakers again, and also to thank the Lubbock Memorial Board for supporting this series of events and also to thank all of you for coming tonight, or indeed if you've been watching us online.